Welcome to the Podkey summary of Marcellus Formation. Today's story is really about one rock unit, doing a surprising number of jobs at once. The Marcellus Shale helps geologists line up ancient history across half a continent, preserves a strange Devonian marine world in flashes, shapes the landscape you can still see today, and in modern times sits right at the center of energy promise and environmental risk. It's also one of those formations where the details matter: how it formed, what's in it, and where it sits. All help explain everything from shale gas drilling to straight river stretches, radon concerns, and even why an old iron industry once grew up around it. The Marcellus is a Middle Devonian black shale unit that stretches roughly 600 miles across the Appalachian Basin, running from New York and Ontario through Pennsylvania, Ohio, Maryland, West Virginia, and into parts of Kentucky and Tennessee. Its thickness changes wildly depending on where you are. In some places in Ohio, it's only a few feet thick, in Canada around 12 meters, and in New Jersey it can reach about 270 meters, or 890 feet. That big change has a pretty straightforward cause. Sediment was pouring into the basin from the east, so the unit built up thicker there and thinned westward toward the Cincinnati Arch. And the name is classic geology. James Hall named it in 1839 after an exposure near Marcellus, New York, which helped cement the habit of naming formations after the places where they're especially well developed. The Marcellus formed during the early Akkadian orogeny, when rising mountains were being worn down, and their fine sediment was washing into a deep foreland trough next to the ancient Catskill Delta. The key condition was anoxia, meaning the basin bottom was oxygen poor. Organic matter, probably mostly plankton, sank into those bottom waters and avoided the usual kind of decay that happens in oxygen-rich settings. That's how you end up with an organic-rich black shale. Measured total organic carbon runs from less than 1% in eastern New York to more than 11% in central New York, which is a pretty big range, and a big clue to how favorable some parts of the basin were for preserving that material. Sea level and basin depth kept shifting too, so the rock record alternates between darker black shale, lighter shale, and limestone beds. Overall, the sequence records a deepening, or transgressive, setting that became both a source rock for petroleum and a seal over more conventional reservoirs. One of the most useful markers in this whole story is the Tioga metabentonite, a regional volcanic ash layer spread across more than 265,000 square kilometers of the Appalachian, Michigan, and Illinois basins. That ash came from explosive volcanism tied to the Akkadian orogeny near what is now central Virginia. At the time, the region was in the southern hemisphere, and southern trade winds carried the ash across a huge area. Geologists can spot it because it doesn't look like ordinary sediment washed in from erosion. The ash has angular quartz grains and distinctive tufaceous mineralogy, instead of the rounded grains you'd expect from normal transport. That makes it a powerful correlation tool, basically a regional time stamp. Although, in very geologic fashion, it's not always tidy, because more than 80 Devonian ashfalls have also led to plenty of miscorrelations. Most of the dominant black shale isn't exactly packed with fossils, but the limestone members are another story. They preserve unusually important marine faunas, including the oldest known diverse collection of thin-shelled mollusks with shell microstructures still intact. The Marcellus also marks the first appearance of goniatites in the fossil record. These were extinct shelled swimmers related to squid, which is a nice reminder that even in a formation famous for mud and gas, the biology is doing something memorable too. Then there's the Cherry Valley limestone, which contains what's been called a cephalopod graveyard. It has lots of large adult shells and no juveniles, which may point to a reproductive site or a place where adults died off together. The fossils also track ecological change through the sediments. In finer, organic-rich deposits, deposit feeders did well, while the coarser upper sediments favored filter feeders. The Marcellus is unusually important in petroleum geology because it plays several roles at once. It's a source rock, it's an unconventional shale gas reservoir, and it can also act as an impermeable seal. Its thermal history changes from place to place. In the north, deeper burial converted oil to gas, while less mature western areas may still be capable of generating liquid petroleum. Its location near East Coast markets helped drive the big drilling surge that began in 2008. And because the gas is trapped in very low permeability shale, hydraulic fracturing is required to get it flowing at commercial rates. There's also interest in carbon dioxide sequestration here. The idea is that the shale can absorb CO2 more strongly than methane, so injected CO2 might help recover additional natural gas at the same time. But that practical value is still uncertain, which feels like a fair summary of a lot of energy technology ideas. Intriguing on paper, complicated in the ground. The same formation that holds gas also comes with some real environmental and engineering concerns. The Marcellus contains uranium and pyrite, which means it can be a source of radon and acid drainage. When pyrite is exposed to air and water, it can oxidize and produce sulfuric acid and gypsum. That's bad news for water quality. And it can also create physical expansion pressures from sulfate minerals. Those pressures have damaged roads, foundations, and other structures built on pyritic shale fill. So the rock can be quiet and stable underground, then become a headache the minute it's excavated and moved around. The Marcellus also leaves a strong fingerprint on the landscape. Weathering and jointing create near-perpendicular fractures that can form sheer vertical cliffs, while weaker beds erode into linear valleys, slope-forming ridges, and surprisingly straight stream segments that follow the rock's strike. A good example is the Delaware River, which follows about a 40-kilometer stretch of eroded Marcellus beds along the Pennsylvania-New Jersey border. Later on, glacial sediment buried parts of that valley beneath the mini-sink. There's an interesting contrast in the soils, too. Soils developed from the Marcellus and the overlying Hamilton shales are deep, stone-free, and useful for agriculture, even though freshly excavated pyritic shale can be a real engineering hazard. Same formation, very different moods depending on what you do with it. Long before shale gas, the Marcellus supported a regional iron industry through hematite derived from the formation. That industry ran from the late 18th century into the early 20th, before richer Minnesota ores pushed it aside. It was resource-hungry in a way that's easy to overlook now. A typical charcoal furnace needed about 2,400 kilograms of hematite and 7.3 cubic meters of charcoal to make 910 kilograms of pig iron, and that meant clearing more than an acre of forest a day for fuel. The industry faded because the ore was discontinuous and uneven in quality, and the coal blast furnaces were inefficient enough to chew through nearby hardwood forests. The shale found other local uses too, including road material, roofing slate, school slates, mineral paint, and fill. So even outside the big headline industries, people kept finding practical ways to put this rock to work. The Marcellus is one of those formations that rewards a second look. Its ancient basin chemistry, volcanic ash, fossil oddities, energy geology, landscape design, and industrial history all stacked into one long band of rock. And that's probably why it keeps showing up in so many conversations. Once you know what's in it, you start noticing the Marcellus everywhere. This episode was generated by Podkey. Create your own at podkey.fm.